Good evening, everyone. Myself, Priyadharshini. I am pursuing PhD under the guidance of Dr. Thangaraju. And now I'm going to give the presentation on topic synthesis and characterization of pure beta phase of bismuth molybdate and European doped bismuth molybdate for photocatalytic applications. So before going to a photocatalytic application, first of all, why we need to go? The release of inadequately treated industrial wastewater is the largest cause of pollution in rivers and oceans. To meet the demands of the current apparel industry, textile industries create wide range of clothes using a variety of harmful chemicals. And these chemicals are basically very serious and toxic to human life. Also, the traditional biological procedures have failed to totally break down these dyes, and the secondary pollutants forming during the breakdown of these dyes become a major issue in many situations. In order to overcome these limitations, we are looking for a low-cost and environmental-friendly method, and one of the methods is a photocatalytic dye degradation. So, what is photocatalytic dye degradation? In the sense, a photocatalyst is a substance that is activated by absorbing a photon and can accelerate a process without being consumed. The process of degrading the dye in the presence of photocatalyst is called photocatalytic dye degradation process. The photocatalyst should be one which has a high surface area and high mobility, small band gap, and it should satisfy the band edges of oxidation reduction. In the picture, we can see that when a light falls on the photocatalyst, the electrons will move from a valence band to conduction band, thereby producing an electron hole pass. In the electron participates in a photoreduction process, thereby reducing the O2 to O2 minus radicals. And the holes takes place in a photo-oxidation process in which the H2O is reduced to OH minus radicals. These radicals will react with our dyes and thereby producing CO2 and H2O as a result of a reaction. So semiconductor photocatalyst, because of the high small band gap and high mobility and tunable band gap, semiconductor photocatalyst is often used as a photocatalytic material. Among semiconductor photocatalysts, bismuth molybdate has attracted because of its catalytic ion exchange and light emitting capabilities. There are three phases of bismuth molybdate, namely alpha, beta, and gamma. In this work, pure and europium doped beta phase of bismuth molybdate nanoparticles were synthesized by sol gel technique in different mediums such as acetic and water to study its photocatalytic performance. So moving to synthesis part, here the bismuth nitrate is dissolved in 25 ml of deionized water, and ammonium heptabolybdate is dissolved in 25 ml of deionized water. Then they are stirred together for 20 minutes. Then 2 millimole of citric acid is added as an binding agent. Then at a temperature of 70 degrees Celsius, ethylene glycol is added to act as an inducing agent. Then after reaction of 12 hours at 70 degrees Celsius, a gel formation of bismuth molybdate occurs. Followed by annealing, we get an pure bismuth molybdate nanoparticles. Similar to this, an europium doped bismuth molybdate nanoparticles are obtained by dissolving an bismuth nitrate and then 0.05 millimole of europium nitrate in 25 ml of deionized water. The other procedures are same as before. And moving to discussion, first, we have taken an XRA analysis for structural confirmation. The observed patterns were well fitted with the standard monoclinic structure of bismuth molybdate phase, and with a space group of P21/N, and its lattice constants are given as A is equal to 11.9, B is equal to 10.8, and C is equal to 11.8. We can see that the bismuth molybdate annealed at 250 degrees Celsius in acetic medium exhibits a low intense reflection peak, but after annealing at 500 degrees Celsius, a sharp peak is obtained, indicating the better orientation growth. Thus, the annealing temperature modifies the growth of the plane in bismuth molybdate. Then moving to same pictures, the samples exhibited an honeycomb-like structure in which many micropore openings are grown perpendicular to the surface. The water-based bismuth molybdate exhibits a spiral-like arrangement compared to the acetic medium, and there will be a large number of pores inside the honeycomb-like structure. Comparing the both phases, europium doped bismuth molybdate nanoparticles exhibits a honeycomb-like structure with micropores. The numerous small dots with a uniform dispersion were identified to be europium nanoparticles that reside inside the walls of honeycomb holes. So photocatalytic dye degradation results are shown. The methylene blue is taken as a model pollutant dye. The absorbance curve of bismuth molybdate synthesized in water and mastic medium is taken at an interval of 1 hour and the experiment is conducted for about 4 hours. The methylene blue's maximum absorption peak intensity is 664 nanometers, gradually shifted, revealing that the methylene blue was oxidized and reduced when a photon collided with a semiconducting catalyst. The dye degradation efficiency graph is shown. Though the water-based bismuth molybdenate degrades the dye effectively within 1 hour, it does not degrade the dye entirely at the end of 4 hours. The addition of europium as a dopant to pure acetic-based bismuth molybdenate increases its degradation efficiency than pure acetic-based bismuth molybdenate. The addition of dopant to pure nanoparticles will increase the active area size of nanoparticles, which significantly help in photocatalytic performance, resulting in enhanced dye degradation. Thus, the 10% of europium doped bismuth molybdenate degrade the methylene blue dye completely within 4 hours. And that's all. Thank you for your time.
Thank you very much.